Hey, grade 10s. So in this lesson, I'm going to go over how to determine the maximum and minimum points of quadratic function. So hopefully, again, I'm hoping some of this is looking familiar to you, depending on what you learned in grade 10. And if it isn't familiar, then that's okay. We're going to go over it today. So our learning objective obviously is to switch in quadratic functions into vertex form, and we'll learn about why that's important. The name kind of says it itself. Vertex form is helping you to find the vertex, which is the highest or lowest point on a function. And we are going to learn how to find the maximum or the minimum values of a quadratic function using vertex form. So a little recap here. There are three different forms of the quadratic function. There is standard form, which is f of x is equal to ax squared plus bx plus c. And it's called standard form because it is going to be normally the most helpful in the sense that we can easily use it to find out what the other two are. So it's almost like our middleman. It's like the form that will help us find all the other ones, right? So standard form is the normal form that you probably learned about the very first week that you learned about quadratic functions. Um, and while it is useful and because it helps us to find the other forms, it doesn't actually give us a lot of information. One of the key points that it does give us is the a value, a coefficient, which basically tells you whether the parabola opens up or whether the parabola opens down. So if it is positive, then it opens up. If it's negative, then we know it's going to be opening down. So at least it helps us with that, right? Helps us identify whether it opens up or whether it opens down. It also is helpful because the c coefficient or the constant term is the y-intercept, and we talked about that in the last lesson. Factor form is helpful because it helps us to figure out what the zeros are. And we can easily identify the zeros by simply looking at the R and S values. By the way, it's not always going to be written this way, and we're going to look at some examples later on where it's actually not going to be factored in this way. There may be a constant in front of the X, and in which case you would have to divide by that. But again, this is something we're going to address in future lessons in this unit. And the last form is vertex form. And the vertex form is the one we talked about probably the least so far, but it is really important. And I'm hoping that this looks familiar to you because this is actually one of the first topics that we discuss, especially when we're talking about domain and range. When you're looking at the domain and range of a quadratic function, luckily, domain, and actually this is true for all quadratic functions, luckily the domain is always XCR. But if you recall, the range is actually not going to be YER. It depends on the vertex. So in order for you to figure out what the range is going to be, you need to know what the vertex is. And the vertex is probably the most easily found by putting it in vertex form. And that's exactly what we're going to be looking at today. We're going to be trying to figure out what the vertex form is because the vertex form can easily tell us what the vertex is. The h parameter right there, the variable right there, is going to be our x coordinate of the vertex. Our k parameter or variable is going to be the y coordinate of the vertex. So that is going to be very helpful to us. So first, before we even get to that, let's talk about perfect square trinomials. So perfect square trinomials, you might remember this when we talked about factoring methods. This is one of the special types of forms that we had that could be easily factored, relatively easily factored. And we learned that the perfect square trinomial was a form where we have a perfect square as the first term there, a perfect square as the last term, and the middle term is 2 times the square roots of the perfect squares, right? And if you are adding the 2 times the square roots, 2 times the product of the square roots, or you are subtracting 2 times the product of the square roots, that will indicate whether you will be adding the square roots or subtracting the square roots. So if you recall, if we have something like ax squared plus 2ab plus b squared, we can factor that out as a plus b, so basically the 2 square roots squared, and we add them up. And if it's written as ax squared minus 2ab plus b squared, we can factor that out as a minus b squared. So we subtract the square roots and then we square them. So I'm hoping that kind of helps out. Now, why is this helpful to us? So let's look at an example. Let's see what is special about this. So we have 4x minus 3. We square it. What that means is, again, just a little reminder, it means 4x minus 3 times 4x minus 3. So we distribute this out. 4x times 4x gives us 16x squared. And then we have 4x times negative 3, which is negative 12x. Then we have negative 3 times 4x, which is negative 12x. And then we take negative 3 times negative 3, which is positive 9. So in total, we have 16x squared minus 24x, sorry, minus 12x minus 12x plus 9. I'm already thinking of the answer here. Negative 12x minus 12x, we know that that ends up giving us negative 24x. So what is special about this is that this expression right here, this quadratic expression in factor in standard form, can actually be factored out, and I'm hoping you understand why it can be factored out like this. Can be factored out as the sum of as the sum of the square roots squared, right? Actually, sorry, difference in this case because we're subtracting right there. The middle term is negative. So what we notice is that we can actually work backwards here to factor it out. We look at the first term and the last term. We take the square root, so we know that the square root of 16x squared is 4x. The square root of 9 is 3. And we are simply working backwards to factor it out. And then we end up getting 4 minus 3 squared. So this is special to us because if you recall in vertex form looks like this. So do you notice any similarity between what we have here and what we have in this form? Well, we notice that vertex form actually has the difference of two perfect squares. Sorry, the difference of two square roots squared, right? So we notice that, hey, wait a minute, this actually looks almost like vertex form. So the conclusion here is that perfect square trinomials can actually be factored out as a binomial squared. So why is this important? That binomial squared actually really resembles vertex form. So what we're going to see here is that when we are using something called completing the square, which is the process of switching a trinomial into the vertex form, which is a times x minus h squared plus k, we're really just trying to figure out how to switch this standard form right here into a binomial squared. We're trying to purposely factor it out so that we get a binomial squared. So our goal is to create a binomial, to create a perfect square trinomial so that we can then factor it as a binomial squared. And why do we want that? Because the binomial squared looks like the vertex form, right? It resembles, it kind of reminds us of vertex form here. So that's really what the idea is. And again, you don't have to understand the whole relevance of why we're necessarily doing this or why it works this way, but I think it's helpful for you to understand the idea that really what we're doing with completing the square is we are manipulating our standard form of the quadratic formula so that we can create a perfect square trinomial. And why do we want a perfect square trinomial? We want a perfect square trinomial so that we can then factor it as a binomial square. So we're trying to kind of play around with our standard form so it can look like a perfect square trinomial. And then once it looks like a perfect square trinomial, we can then factor it as a binomial squared. Okay, so the difference of the square roots squared. That's basically what we're doing. So I'm hoping that idea makes sense. Again, you don't need to understand this. I will never ask you in a test, how does completing the square work? I won't ask you that, but it's good for you to understand. And I think if you understand this, it will make the whole concept of completing the square relatively easy to follow. So completing the square is basically the process that we follow so that we can switch it from standard form to vertex form. And the name kind of says it itself, right? We're doing that so we can find the vertex. So we're trying to switch from standard form to vertex form, and we do this by completing the square. And it's called completing the square. Again, the name should kind of help you out. You're completing the square, meaning that you're trying to create a perfect square trinomial on purpose. So you can then factor it as a binomial square. So how do you do this? Well, let's go step by step. What you're going to do first is you're going to group the first two terms together in brackets, okay? And not in a bracket, in brackets. So the third term, the constant, is left by itself. Now, I want to explain one small thing. If there is a different way to do this, and it is possible for you to do this, you can also common factor out the leading coefficient first before anything else. And then you can continue the steps as we have them. But I personally like to follow this step. You don't have to do it exactly the same way. And again, completing the square, just like factoring, there are different ways to complete the square, okay? There is technically a slightly different way to do this, but I'm gonna show you what I think is the easier way, okay? So what we're gonna do is group the first two terms together. So that means, as an example, and I'm gonna give an example so you can actually see it concretely. What we're gonna do is we're simply gonna put brackets around just the first two terms there. And the third term is just gonna be left on its own, okay? Pretty simple. Then what you're gonna do is you're gonna look at the first two terms there, and you purposely want to create a perfect square. So what does that mean? That means that you want you want to add on a third term right after it that is a perfect square. So how do you create a perfect square on purpose? Well, and again, you don't have to understand why this works, but I'm hoping that it does make sense based on the other examples we did. If you recall, the middle term was 2 times the product of the square roots, right? So if you know that the middle term is 2 times the product of the square roots, then you can actually work backwards to figure out what one of the perfect squares would be. You would do the opposite of multiplying by 2. You would divide by 2. So you take the middle term, divide by 2, and then you're simply going to take that and square it so you can create a perfect square. So you're basically doing the opposite operations. Right before, when you had it, and I'm going to go back to the first example we did here so you can compare. Notice that when we had 4x minus 3 squared, when I expanded this out, I noticed that I would take the product of the two square roots, so 4x times 3, that gives me 12x, and then I multiply by 2, that gives me negative 24x, right? So what we're doing is we're saying just work backwards. Take that middle term here, divide it by 2, and then you're simply going to take that answer and then you're going to square it. That's all we're saying there, right? So you divide this by 2, which gives you 12x in this case, and then you square that. Sorry, you take just the coefficient itself. So take 12, so half of 24, which is 12, and then you square that, and then you end up getting, and again, it's negative, but when you square, you end up getting a positive anyways. You end up getting positive 36. So then that means that we would be adding on a 36 there. Now, going back to this example here, what we're simply doing, again, I hope it makes sense. So you're basically working backwards. So you're going to be dividing the middle term by 2, right? And then you're simply going to take that middle term divided by 2 and square it. Then what you will do is you will add that value to the equation in the brackets, and then you're going to be subtracting that value to balance out the equation. And the reason you're doing that, again, this goes back to basics in algebra. You cannot simply add a value to a number. So if I have an equation like this, if I know, the left side equals the right side, I have two equivalent expressions here. If I add a 2 here and then I add a 2 here, it's balanced, right? But if I only add a 2 to this side, that's not going to keep it balanced. So to counterbalance that, I need to be able to add I need to be able to add the inverse of that, right? So I take the positive 2 and then I simply subtract the 2, right? So I know that these are the opposite numbers there. So that's really what I'm doing here is I'm taking the middle term, dividing by 2, square it. I add that value and I also subtract that same value to keep it balanced. So here's the example so you can see it clearly. I take my middle term, the coefficient, which is 12. I divide by 2, which gives me 6, right? So doing the math here, I have 6 squared. 6 squared is 36. And then and then of course, I just mentioned this, I can't just add a 36. I can't just magically do that. I have to also subtract the 36 to balance it out. So that means that 12 divided by 2, which is 6, is then squared, and I get 36. And that means I'm going to counterbalance it with the positive 36 there. So this ends up giving me y is equal to x squared plus 12x plus 6 squared minus 6 squared, and then of course outside the brackets plus 30. So far, let's simplify. I mean, I have the answer here, and really it's quite easy to do here. All I have to do is write y is equal to x squared plus 12x plus 36 minus 36 plus 30. So everything looks good so far, although you're probably thinking, why am I creating more terms instead of making less terms, right? You initially started with 3 terms, now I have 5. That seems kind of complicated, but don't worry about this. We'll figure this out. So what we notice right now is, and I hope everyone notices this, that this is a perfect square trinomial. And notice that it's a perfect square trinomial because this is a perfect square, this is a perfect square, and 12x is 2 times x times the square root of 36, which is 6. And if you're wondering, wow, how did I create that perfect square trinomial so perfectly? No pun intended, right? Um, I'm hoping it's pretty obvious how we made that. We did that on purpose, right? This isn't a coincidence. You shouldn't be looking at that and being like, wow, how did we do that? Well, we did it on purpose, right? We purposely wanted to create this perfect square trinomial, and we did that, which is great. So now what we're going to do is we look at that and say, okay, x squared plus 12x plus 36 is the perfect square trinomial we wanted. Unfortunately, this negative 36 over here is not going to be part of that group. We should exclude it from that group. So what we're going to do in our next step is simply take the negative copy of the perfect square. And I always say the negative copy is just basically the negative the opposite of the perfect square that we created. And we're going to write it outside of the brackets. So then what you do is you simply write the negative 36 outside of the brackets. You have negative 36 outside like that. And then what you're going to do now is you're going to factor the perfect square trinomial that's in brackets. And you're going to do this using the shortcut, which we just learned about, right? We already learned that, this is a perfect square, that's a perfect square, and the middle term is 2 times the product of the square roots. So then that means that we end up getting x plus 6 squared minus 36 plus 30. Now, how did I factor that out? Pretty easily. Well, again, the square root of x squared is x. The square root of 36 is 6. So then you put them together, and again, you always keep the sign of the middle term. So in this case, we're going to be adding the square roots, and we square them, square that sum. And the negative 36 and the 30 are still next to each other. So how do I simplify this? Well, luckily, they are both constants, so it's pretty easy to do. All you need to do is add or subtract them. And in this case, we add them. Negative 36 plus 30 is negative 6. So then we end up with y is equal to x plus 6 squared minus 6. And that is our vertex form. So looking at this here, we know this is our vertex form, which means that we can pretty easily identify what the vertex is. The vertex is negative 6 and negative 6. This is the x coordinate of the vertex. This is the y coordinate of the vertex. So as a general case here, and I wouldn't worry too much about this. This is not necessarily something I'm going to ask you on a test, but I hope you understand this because this will be really important when we look at the quadratic formula. To complete when you complete the square in general of a function in the form ax squared plus bx plus c, we basically are going to follow the exact same steps, except that you're going to do this for variables. So the only difference is that whatever you would do to numbers, you are going to be doing to variables. And I want you to understand this. Like I said, it won't be on a test, but I want you to understand this because this is really at the core of how we find the quadratic formula. So I want you to understand where this is coming from. So what we do here, if these were regular numbers, we'd follow the same steps. You put brackets around the first two terms. And one thing you're going to notice is that because there is a leading coefficient that is not equal to 1, we didn't do this in the last step, but we are going to do it here. We common factor out the a from just the first two, right? So we're going to common factor out the a. And why do we do this? Well, we're doing this because we want to make sure that it's a perfect square trinomial. So if I keep the a there, it's not a guarantee it's a perfect square trinomial. If I take out the a, then I end up with just x squared. And we know that we can definitely take the square root of x squared on its own, right? We end up just getting x by itself. So we factor out just the a from the first two. So then you end up with x squared plus b over ax plus c. Then what I do is I take my middle term, which is b over 2a, and I b over a, and I take it and then divide it by 2. So b over a when I divide by 2, doing a little bit of math here, this ends up giving me b over a times 1/2. And I know that b over a times 1/2 becomes b over 2a. And what am I doing here? I'm simply taking that middle term and squaring it. Now remember, I have to create a negative copy of that. So what I do in this next step here is I take my negative copy, which by the way, I forgot to include, should have been included in this line right here. And I'll make the change on the PowerPoint. I take that negative copy and I put it outside the brackets. So I'll just erase that there. I take that negative copy, put it outside the brackets. But when I do that, remember that this is going to be multiplied by a. The reason it's multiplied by a is because when I put it outside of the brackets, remember, it was still being multiplied by a, by the leading coefficient a there, right? Because this was multiplied by the whole entire set of brackets. So I actually made a mistake here. I forgot to include the negative copy there. So I'm actually going to add that right now so it doesn't confuse you there. So it's going to be minus b over 2a. Sorry, let me just add that on here. I'm going to add it before I forget. Okay, perfect. And I'm just making sure that this is the negative copy so you understand that. So it's going to be negative b over 2a. Sorry, let me just fix the brackets. I just don't like the way it's written here. Just want to make sure that it's a large bracket here so you understand that. Perfect, okay. Sorry guys, I'm just making small changes here so it actually looks a little better and easier to read. Okay, so now we have this, perfect. Okay, so now it looks a little bit more clear. Okay, so going back to this, so hopefully everyone can see so far what we're really doing is we're simply creating a perfect square. Like I said, we're creating that perfect square on purpose. We take the middle term coefficient divided by 2a, divided by 2, and then we square it. And then what we're doing is simply finding a negative copy of that. So that negative copy is then, like I said, multiplied by a, which is why we get minus a times b over 2a squared. And then what we notice next is that we can factor this out using perfect square trinomial factoring. This is a perfect square, and this is a perfect square. So what is the square root of b over 2a squared? Well, I hope everyone understands that when you take the square root of a square, it actually cancels out and we end up with b over 2a. And again, the reason for that is because squaring and taking the square root, they are inverse operations. So then we end up with b over 2a as our square root, right? So we have x plus b over 2a, and again, we're adding because we keep the sign of the middle term, which is b over ax. And then notice here what ends up happening. We end up getting, and I'm going to do this on the side, we have a times b over 2a squared. And this requires a little bit of exponent laws. If you recall from exponent laws, we are allowed to apply the exponent 2 to the b, variable b. We apply it to 4, and we apply it to a. So this ends up giving us a times b squared over 4a squared. And when we do this, we actually end up with a times b squared over 4a squared. And then in our next step, we notice that the a here will actually cancel out with one of the a's in the denominator here. So we end up with b squared over 4a, and it's negative there. And we know that we can factor this out using the perfect square trinomial factoring. And then we end up with a times x plus b over 2a squared minus b squared over 4a plus c. Now, everything looks pretty good, but one thing I would change is simply to simplify this expression right there. And again, this is really a term. It's just a term. It's a constant in itself, right? So it's going to be a number. So what we're going to do is find a common denominator, which is 4a, and this should remind you of rational functions when we were adding and subtracting them. So then that means I multiplied. So of course, if I'm going from C to a denominator to a fraction that has a denominator of 4a, then I know I need to multiply the numerator and the denominator by c. So this ends up giving us 4ac, right? So we get 4ac over 4a. And then of course our last step here is we simply add the denominator, add the numerators, and this ends up giving us minus, 4ac minus b squared all over 4a. And I am going to then, and I don't want to go into too much detail about this, but then what I would do next is simply, I could factor out the 4a, and that gives me a more simplified version of what the y coordinate of the vertex will be. So the reason I'm going over all this, and you're probably wondering, why did I go through all this detail? Remember this because it will help you understand when we try to find the quadratic formula. Now, I will not put this on a test, so I'm just going to be clear on this. Not on a test, okay? Not on the test. So don't worry about trying to memorize this. It's not going to be on a test, I promise you that. But I hope you actually try to follow it and understand it. I'll be quite honest, if this is the only thing you don't understand in the note, that is totally fine. I'm not going to be upset, and I don't think you should be worried. It's not going to be on the test, but I do think that it is worth you going through this and trying to see if you understand how I was able to simplify it to this form here. And again, this will help us understand the quadratic formula when we get to that. So let's do 2 other examples here. So we have completing the square in this first one. Let's start with the first one here. We have x squared minus 6x plus 17. So first step, I'm going to put brackets around the first 2 terms, which we just did here. Then I'm going to take my middle term, which is negative 6, and I'm going to divide it by 2, and then I'm going to square that. So when I do that, I end up getting negative 3, and I square it. And remember, even if it's negative, doesn't matter. In the end, it's going to be positive when I square it. So then I end up getting x squared minus 6x plus 9. And then remember, I have to make a positive copy of that number and a negative copy of that number. So it's going to be positive 9 and minus 9. The reason I do this is because, remember, I'm not allowed to just add a 9. I have to make up for it by subtracting a 9 as well. So what I do next is I look at this and say, there are 3 terms there which resemble a perfect square trinomial. So I'm going to focus my attention on those 3. And then the 2 odd man out, or the terms that are a little bit odd, I'm going to leave them out. I'm going to purposely kick them outside the brackets. So we have x squared minus 6x plus 9. The negative 9 gets moved over outside of the brackets with the 17. And then I look at this and say, can I factor this out? X squared minus 6x plus 9. Absolutely. I can factor that out using perfect square trinomial. The square root of x squared is x. The square root of 9 is 3. So I'm going to write this as x minus 3 squared. And the negative 9 plus 17 is going to simply be, I can simplify by adding them. So negative 9 plus 17 ends up giving you, a total of 8 in this case, right? So we add on the 8 there, and then we end up getting x minus 3 squared plus 8. So I basically factor this out as a binomial squared plus a constant there, which we hopefully recognize as vertex form, right? And there is our, like I said, there is our vertex form of that quadratic equation there, our expression. Let's look at the next one. So we have 2x squared plus 12x plus 11. So what do we do to complete the square? So we put brackets around just the first 2 there, first 2 terms. And what we are going to notice is that in this case, when we put brackets around the first 2, we don't actually end up with something that could become a perfect square trinomial. And the reason for that is because even if I created a perfect square trinomial, I could try, but even if I tried my best to create a perfect square trinomial, I can't do it yet. And the reason I can't do that is because the first term itself, 2x squared, is not a perfect square, right? And it's not a perfect square because obviously the square root of 2 is not a whole number, right? So what we need to do in this case is factor out the 2. We need to factor out the 2 in order for it to then become potentially a perfect square trinomial, right? So we take out the 2, and then we end up getting x squared plus 6x. Now we look at this and say, could this potentially become a perfect square trinomial? Absolutely, because the leading coefficient is 1 and the square root of 1 is 1. I can definitely work with that. So then we end up getting 2x squared plus 12x, and of course I factor out the 2, and then just the 2, I only factor out the 2 from the first 2 there, because again, the 11 is kind of isolated on its own. So then we end up getting 2x squared plus 6x plus 11. My next step here is I'm going to follow the exact same steps as before. I'm going to take the middle term, divide by 2, which is ends up giving me 3. And then, of course, I'm going to take 3 and I square it. That gives me 9. And then I have to subtract the 9 as well. So what I do now, when I bring out the negative 9, and this is where it becomes a little bit different than before. So far I have 2x squared plus 6x plus 9 minus 9 plus 11. But we already discussed this. I look at this and say, this is a perfect square trinomial. This is what I want. But that negative 9 is kind of bugging me. It shouldn't really be there. So what I want to do, just like we saw in the last example, I want to bring that negative 9 over. Unfortunately, it's not as simple as the other case because I notice that the negative 9 itself is actually not just negative 9. It's actually negative 9 times 2. And how do I know it's negative 9 times 2? Because I know that the 2 is outside of the brackets. So going back to when we talked about multiplying a monomial by a binomial, or any sort of trinomial, whatever it might be, when I multiply by a monomial, that means that every single term inside the brackets needs to be multiplied by that monomial outside. So the 2 is then multiplied by negative 9. So it's not just going to be a negative 9 being pushed out. It's going to be negative 18 because I multiply the 2 times negative 9. So when I bring it outside, again, this is what's going to go in here. It's going to be 2 times negative 9. I need to figure out what that gives me. That gives me negative 18. That means that the negative 18 is going to be placed outside the brackets. And why is this all looking normal so far? Because these three terms create a perfect square trinomial, which I can work with. There's just a 2 outside. And again, I have to remember that when I bring that negative number outside, I simply multiply by the leading coefficient, which was still in front of the brackets. And I hope that kind of makes sense so far. We didn't have to do that before, by the way, because our leading coefficient in the other case was actually just 1. So when the leading coefficient was 1, when we brought the negative 9 over, we didn't have to multiply by 1 because multiplying 1 times negative 9 didn't do anything. But in this case, I had to do that. So that's why I changed. And if you look at the example when we looked at how completing the square works in general, you notice that we kind of did the same idea, right? We had to multiply by the leading coefficient of a. So I hope that makes sense so far. So our last step here is to simply add these two numbers together, negative 18 plus 11, which ends up giving us negative 7. And that means we end up with 2 times x plus 3 squared minus 7. And that is our vertex form. And looking at this vertex form, we can hopefully tell that the vertex would be negative 3 and negative 7. And that is our vertex there. So how do you check if the answer is correct? Well, luckily checking the answer is actually a lot easier. You just expand and simplify, which we learned how to do. So if you recall how to multiply, but if you can remember how to multiply binomials and simplify expressions, then this is actually quite easy. All we're doing is multiplying the binomial squared. The only difference is it's a binomial squared, and then we expand out our expression, and then we simplify. So in our case here, what we're going to do is expand all the brackets. So we have x plus 3 squared, which is x plus 3 times x plus 3. And I think I gave you a question like this on your test. The last test, I basically, made it true or false. X plus 3 squared, remember, it's not going to be x plus 3 plus 9. Sorry, it's not going to be x squared plus 9. It's going to be x squared plus the middle term, which is 6x plus 9. So what we're going to do is expand this out. So we have x plus 3 times x plus 3, which becomes 6x. And by the way, I shouldn't have put it twice. So let me just erase that. Let me erase it here. So we have x plus 3 times x plus 3, which is x squared plus 6x minus 9, plus 9. And then what I do next is simply multiply each of these terms by 2, right, outside of the brackets. and then we end up getting 2x squared plus 12x plus 18. I subtract the 17, and then I end up getting 2x squared plus 12x plus 11, and that's it. And the last thing I wanted to go over is just a brief little overview how to switch between different forms. Now that we learned about vertex form, standard form, and factored form, it's important for you to know how to switch between them. So I'm hoping this chart kind of helps you out. If you want to switch between standard form, let's start with the easy one, standard form and factor form. I'm hoping everyone understands that this is quite simple to remember. You simply factor, right? And we know how to factor. We've done it a lot, so I'm not going to go over that as much. You factor using sum of product, you use perfect square trinomial factoring, difference of squares, whatever it may be. If you want to go from factored form to standard form, then we know we need to simply expand and simplify. So what that means is we multiply our binomials. So as an example, let's say that this is the factor form. I'm making this up here. We simply expand it out, collect the like terms, and write it in the form of ax squared plus bx plus c. So remember, you write it in order from largest exponent to the smallest, from the largest power to the smallest power. To go from standard form to vertex form, we actually just learned this today, we simply complete the square. And so completing the square really just means how can I rewrite the standard form so that I get a binomial squared? That's really what you're trying to do there, right? You're trying to get a binomial squared by writing it as a perfect square trinomial so you can then factor it easily. And then, of course, if you want to go from vertex form to standard form, we just saw that, you simply expand and simplify. So you take your vertex form, and I'm just giving an example here, 2x minus 3 squared plus 18. You simply expand this out as x minus 3 times x minus 3. You multiply by 2, you multiply the whole expression by 2, and then add the 18. So you expand it out and simplify to get into standard form. Great question is how to go from vertex form to factor form. Well, to be honest, there really isn't a shortcut. And this is where standard form is helpful. So if you want to go from vertex form to factor form, there's no easy way to go around it, or factor form to vertex form. So what you do is you have to go from vertex form to standard form, and then from standard form to factor form. So it's a bit of a longer way to go around it, but you have to use standard form as kind of your middle ground. It's kind of like the highway to get to the other two. Okay, so we have to go through standard form first before you go from vertex form to factor form, or factor form to vertex form. And that is basically it. And there are the questions, so good luck.